Okay, so let's start. This is the moving guide. Again, this particular concept is very important and straightforward questions going to be framed on this particular concept or subtopic, like conversion of moving coil galvanometer to ammeter. Most of the time, conversion of moving coil galvanometer into the voltmeter. Okay, so what we already done in the previous class, or you can say previous classes, you're going to find something or many things related to that. So don't bother about it because that is going to be correlate, for example. Okay, so let's start with, this is your recall torque. We already know, everyone, torque is that can measure an object to twist along the axis is measured as a torque, or you can say rotational force is also known as a torque. If anyone have a doubt in this, so rotational force, or you can say rotational force, or yeah, the force which is going to rotate any particular object is known as torque. Very basic example, very simple thing. For example, it is your a door. In that particular door there is a hinge, or you can say one side is fixed. So if you apply any particular push or pull on this particular door, so it is going to rotate in this way, either on about its axis, either in this way or either in this way. So this is your rotational force, or also known as torque. Is this clear, everyone? So we already know this thing since class 11. If anyone don't know, so now he or she can clear it out. Is this clear? In linear kinematics, force is what causes an object to accelerate. Torque is also responsible for the angular acceleration. As a result, torque can be defined as a linear force, rotational equivalent, or you can say directly rotational force. The axis of rotation is the point at which the item rotates. Torque is the property of a force to turn or twist. As simple as that, nothing more than that. Clear, everyone? Okay, moving ahead. Example, when a person pull close the door. I already given this, so just brief then. Door remains static because it does not rotate despite the force applied, because there is no acceleration. Paddling a bicycle at a steady speed is likewise an example of static torque. Means whenever you paddle, whenever you open or close the door, so in that particular thing, the object is not going to accelerate, but it is going to angular accelerate or twist. At that twist and that force, which is going to rotate any particular object, is known as torque. Why we are doing this, why we are learning this from the very basic? Because in the magnetic term we are going to see, I already given to this, maybe or maybe not, but still, magnetic dipole moment of a revolving electron. So I think I discussed this thing, but still for a revision, the negatively charged electron revolves around a positive charged nucleus in a circular orbit. According to Neil Bohr's atom model, an electric current is made up of a rotating electron in a confined channel. The anti-clockwise travel of electron generates a conventional current in the clockwise direction. What it means in general, because we need to understand properly this thing, so that it can help us out whenever we are going to learn about Bohr magneton here as well as in Bohr model. Is this clear, everyone? So as we know, this is our nucleus, or in nucleus we have a nucleons, means proton plus neutron. So this is your proton, this is your neutron, and your electrons is revolving in this. The revolution of electrons are the same as the revolution of Earth on its axis also, or surrounding in this particular nucleus also. So due to the motion of charge, it creates a current, and when current is in the motion, so it creates a magnetic field. Or whenever we have a magnetic field, so we have a magnetic dipole. Whenever we have a magnetic dipole, so we have a magnetic dipole moment also. Is this clear? Initially, is this clear or not? Again, if we have a charge in motion, so it creates a current. If current in motion, so we have a magnetic field. If we have a magnetic field, so we have a magnetic dipole, because magnetic monopole cannot exist. Okay, so this is your charge and charge in motion. This ratio you can say motion, current, and this is in motion, magnetic field. And we have a magnetic field means magnetic dipole. Magnetic dipole, because we have a north pole and south pole all together every time. This is your north, this is your south. Clear? So that can be generated due to the rotation of electron also. Or if we have a magnet, so we have a magnetic dipole moment also. How so? What is the formula? How we are going to define? We are going to discuss in the next slide. So magnetic dipole moment of a revolving electron. So first of all, we talk about current, then we talk about time, then we talk about current of an electron, and then obviously this magnetic dipole moment mu equals to Ia. A is pi r square, because that is we take as a spherical shape in general, or then sphere have a radius r, and then simply we find the formula. Is this clear, everyone? Or should I repeat again this thing? Focus here, because if you understand this particular terminology, so everything is easy. As you know, we have this as a sphere. Okay, so this is the center of a sphere and this is the radius of. So this particular electron doing motion or having a motion of two kinds. For example, on its axis also, that is known as spin momentum. We discuss more general in atomic theory or in Bohr model. For example, take a analogy as a earth. Like earth is rotated in the surrounding of a sun, as well as earth is rotating on its axis, due to which we have a day and night. In a same sense, this particular electron doing a motion on its axis, okay, on its axis like this, in a same sense, like earth, this spin half and this one, and this is going to rotate in this way also. Okay, just a minute. If this is your nucleus, so due to these two motions, the electron generate a current, and when generate is it, I mean when this current is in the motion, okay, so due to this motion, electron generate a current, or when this current is in the motion, we have a magnetic field. Is this clear, everyone? Or whenever we have a magnetic field, so we have a magnet. As simple as that. We treat as a magnet. So due to this magnet, we need to find magnetic dipole. So obviously we need to find current due to electron. And if we find current due to electron, then using the formula of magnetic moment, simply mu equals to Ia or m equals to Ia. Ia stands for I stands for current, A stands for area. We can find the magnetic dipole moment of a revolving electron. And believe me, this is very, very important, not only here, but in atomic physics too. Atomic physics means in atomic chapter also, which is going to be the second last or third last of the class 12. So that is going to be coming back again. Is this clear, everyone? Is this clear with everyone? Just type yes if it is clear. So, okay. So simply, as we know, current definition, I equals to charge by T. So here we have a charge of an electron, which is Q equals electronic charge, because we talk about electron here. And then T is, again I am drawing this, then T we take a time period, because for this particular kind of spherical shape, this is your radius, this we take as a radius r from the nucleus. If we take this as a radius, okay, this is your radius, and suppose it is the electron moving in this way, or it is also moving, okay, for better picturization, it is also moving around this axis. Clear? So due to these two motions, it generates current. Due to the motion around its axis, it generates current, and due to the motion around in this particular circular loop, in this particular spherical way, it generates magnetic field. So first of all, we need to find the current. Is this clear? So current is nothing but E by T, where E is the charge of an electron and T is the period of the electron, where V is the electron's orbital velocity. So then As we simply know, time period nothing but displacement or distance upon time. So distance beta here is circumference, which is 2 pi r upon v, and charge is simply E. So from here we can find current due to the motion of an electron in a atom. This is the current due to the motion of an electron, in an atom. Is this clear, beta? This is important one again. Is this clear, Harimesh? Everyone, if I'm asking, so that is the general question. Okay. Is this clear, beta? And please, it is requested as always, turn on your cameras. Everyone. Everyone means everyone. Okay. Only 2, 3 I can see the faces. So please, it is requested to you. Everyone can turn on your cameras. So that is your current, and simply then there will be an orbital magnetic moment. We already talk about a lot for this orbital magnetic moment, mu L. L is specifically due to, okay, I just give you a hint. There are quantum numbers N, L, M, or S. What it is in general, N is the principal quantum number, L is orbital, M is magnetic, or S is spin. We talk about it in great detail when we are going to discuss in the atomic physics, or maybe you hear these terminologies in chemistry also. What is quantum numbers, or you can say quantum numbers. Dependent on that, we have the whole atomic physics. Okay, L equals to n minus 1. Yes, it is. Okay, L equals to n minus 1, S equals to plus minus half, M equals to plus minus something. The formula is, so, but it is quantum numbers. Okay, on the basis of that, we can say in which particular period, or in which particular circular shape or period, SPDF. Okay, periodic, not periodic. S stands for spherical, P stands for something look like this, and then D stands for dumbbell, and then F stands for folded dumbbell. Okay, these are the names. We already discussed this thing. I mean, in chemistry, I think we teach this particular terminologies in 11th class. In physics, we teach in this a little bit, not much. So that is your due to orbital magnetic moment, due to this particular orbit, due to this particular quantum number, V stands for just L, nothing more than it. A again, because it is a spherical orbit, or not periodic one, or not P. P stands for what? Right now it doesn't, I mean, that particular name is not striking me. Someone, if you know, so please let me know. S stands for spherical, D stands for dumbbell, or P for what? There is one word for P also, and F is folded P. Okay, so A is area simply, and this is your then magnetic moment due to the orbital, or you can say due to the electron revolving due to in its particular orbit. So that is again important. So this formula you're going to use again and again. Okay, it is important too. Wait, I can search for you SPDF name. SPDF orbitals full form. That is going to be what is SPDF? Please tell me, anyone. I want to know. Yes. Cubic general. No, I don't know. D shell, L shell, C block, no. Okay, let it be. Right now we are not going into the depth. Okay, so there are, I mean, these are the names. S for spherical, P for periodic, or there is specific name. Right now I just forgot it. So this is all about your formula for the magnetic movement due to the revolution of electron in their particular orbits. Is this clear, everyone? Okay. Moving ahead, consider the mass of electron to be m. I mean, we can put this particular term in this L, and then this L by m, or you can say mu by L, is we can say that E upon 2m. That is one terminology known as gyrometric ratio also. Mu L upon m, or you can say L by m. So I mean, why should I say this name or term gyrometric ratio? L by m, the ratio of angular momentum to the mass, because we are going to discuss one class assessment, or you can say one numerical question for that. So suppose that is very easy. Instead of, I mean, we can MVR, we just converting this particular formula into this one, multiplying and divided with the m, nothing more than that we are doing in this. Okay, so as we already discussed, as we already know, we have a this one EVR upon 2. So if I'm multiplying and divide with mass only, so what can I do? MVR is my angular momentum, which is L, and E by 2m is the specific ratio for any particular what? Charged particle. Is this clear? So that is directly dependent on the L, which is angular momentum. So consider the mass of the electron to be m, divide and multiply with the mass. So this MVR gives me angular momentum, which is L, and then this is fixed. So the electron's angular momentum L around the central nucleus is MVR. So this magnetic dipole moment of a revolving electron can be put into this terminology, can be put into this formula also, which is more important. Is this clear? Okay. So this, from this particular formula, what you get, important one, if you know this angular magnetic dipole moment mu L, so you can directly find E upon 2m L. So you can directly find this L, angular momentum. How? So L is then mu L into 2m by E, as simple as that. Okay, this is clear. And this L is angular momentum. This L1 is better, nothing but angular momentum. So these are the small conversion of formulas related to each other. Now you think, I mean, why this is going to be important? If you have done all the class 11th and 12th, and only you have mu L or other L only, and there is a numerical value, or there is a numerical problem you get, like find the angular momentum, simple, and when there is mu L is given, okay, magnetic dipole moment of a revolving electron is given only. So on the very first hand, you are going to confuse what the particular formula I am going to apply, and that is very easy formula, as because E you know, and mass of electron you already know, isn't it? So that is why it becomes very important. Is this clear, everyone? Is this clear, Jyotsna? Okay. Because you are typing something. Okay. So that is why these small formulas are very important. Okay. Moving ahead. Then there is a gyrometric ratio. So as I already discussed, mu L by L is, which is E upon 2m, is known as gyrometric ratio. And it is a constant thing, as we already know, E by 2m, because E charge is fixed, m of electron, mass of an electron is also fixed. Its value is 8.8 into 10 to the power 10 coulomb per kilogram. As simple as that, because E is coulomb, m is mass. So the angular momentum according to the Bohr has only a discrete set of values given by the equation, which is I equal, or equal, that is not I, it is L. It looks like I, but it is in general L. Let me draw that. L equals to NH by 2 pi. Here N is a natural number. That is not natural number. Here N is a quantum number, or you can say principal quantum number, or you can say natural number also, 1, 2, 3, 4, 5, 6, anything, and h is a Planck constant. Okay, according to, okay, let me give you the proper written thing. According to Bohr theory, according to Bohr model of atom or Bohr atomic model, what we can say, L, angular momentum, is mh upon 2 pi. What is the meaning of this? Rutherford gives us this particular theory whenever, due to his famous experiment of Rutherford gold foil experiment. In between of a atom, there is a center where maximum number of mass is going to be attached. This is known as your nucleus, and electrons revolving in the surrounding of it. But he predicted according to the classical mechanics. What is the classical mechanics? Like Earth is revolving. So we know this thing, whenever any particular charge particle is revolving, so it generates, or you can say it dissipates energy. Dissipates energy means energy is going to be fall down. Clear? So he cannot predicted that, like if it is going to be fall down, so each particular atom is going to be shrink in this way. Okay, wait. In this way at the center, or if your electrons falling down at the center, so positive negative gives you 0 and atom is going to be collapsed. But atom is not collapsive because we have an object in nature. So this particular theory is enhanced or improved by Bohr, in which he suggests these electrons not moving in any particular orbit, but they are moving in certain orbits known as stationary orbits, in which the angular momentum is this. And from here we have a quantum mechanics birth or origin. Is this clear, this picturization? Okay, I am just sharing this story right now because when we are going to discuss atomic theory, or you can say Bohr atomic model, we are going to discuss in a whole sort. But why it is important, what is the meaning of this? So just for a glance, just for a picture, I am telling you guys. Is this clear? Clear, everyone? Okay, so that is the sense. Okay, now substituting the formula of L into the formula of mu L. So if you putting here, as we know again, mu L is nothing but E upon 2m into L. This is your angular momentum. According to Bohr formula, if we are going to put L, which is nh upon 2 pi, so that is our formula for this one. Which one? Magnetic dipole moment. Okay, magnetic dipole moment of a revolving electron you can find in this way also. So the minimum value of magnetic moment is obtained when we put n equals to n, as simple as that. And that is the important thing. This is known as your Bohr magneton. So directly they ask the formula for Bohr magneton. And believe me, when they ask the formula for Bohr magneton, no one understands what Bohr magneton is in general. Even they don't know what a Bohr magneton. So when you don't know the term, so how you can just remember, or how you can write which particular formula is going to be the correct one? Is this clear again, or should I start from the beginning? So the beginning is, we have an atom. In atom, electrons is going to rotate. Okay, so due to this rotation of electrons, we have a current. But electrons rotate not only in this way surrounding the nucleus, but on the axis. This is my put or assume like your pen as the axis. So that is going to rotate in this way also. So due to these two rotation, we have a magnetic field due to the electron rotation. And when we have a magnetic field, so we have a magnetic dipole moment also. So magnetic dipole moment initially, that is this one, mu L equals to IA, IE, I, which is current, EV by 2 pi r, and A pi r square simply. Then moving ahead, we can put, and we can multiply and divide with the mass. So it becomes into this particular terminology, magnetic dipole moment of an electron, mu L is E upon by 2m, which is L. L is angular momentum, and then this E by 2m is known as gyromagnetic ratio, or you can say mu L by L. Magnetic dipole moment upon angular momentum is a ratio, as we know that, and so it is known as gyromagnetic ratio, which is the having the value 8.8 into the, it's have value 8.8 into 10 to the power 10 coulomb per kilogram. According to Bohr model, Bohr has only a discrete set value of n. What is the meaning of that? These electrons cannot revolve in any particular orbit, but they can revolve or rotate in a certain specific orbits. These orbits define, designed, or you can say accommodated to these electrons on the basis of this angular momentum, which is nh upon 2 pi, where n is a principal quantum number. So putting L equals to nh upon 2 pi, we have this, which is the minimum value of a magnetic moment obtained whenever an electron is rotating, revolving in an atom, and that is known as Bohr magneton. Is this clear? Is this clear, beta, everyone? Just type it if it is, or if you have any question queries, so you can ask me right now. So tell me one thing, is there any particular exam festival is going on in your cities or something? Or, I mean, you also go for your summer vacations? Because I can find the number of students are very less from the last one or two classes. So is there anything like, because it's your last chance to go on a summer vacation, so maybe you guys going on summer vacation, because after this year there is no summer vacation, it's going to be done. So if you are going, I think because of any extracurricular activities, like what, games, or I mean vacation trips or something, what? Because I can see only few names in a continuity, and then we have a good amount of students in this particular batch at least. And then they come in the PTM, and then they ask questions like, why our child is not performing well? Because he or she is not attending the classes. As simple as that. So how he can or she can perform well? Just I mean, just by seeing my, not only my, but other tutors also recording or class assessment or homework. Okay, so that is important again. Okay, whatever the reason is, I think and I hope and I believe from the next to next class, which is in July, the amount or the strength of students going to be again on a proper note. So this is magnetic dipole moment of a revolving electron, the value of Bohr magneton, because as we know, Bohr magneton is also constant, E is constant, H is constant, phi is constant, M is constant. Okay, so we have a Bohr magneton. Let me write it down. Bohr magneton, which is mu L equals to E H upon 4 pi M, if I'm not wrong. Yeah. Okay, so we, as we know, E is constant, everything is constant in this particular formula. So we can find, or we can write the number. Number is what? Proper value assigned to this. The value of Bohr magneton is determined to be this much, 9.27 into 10 to the power minus 24 ampere per meter square, because as simple as that, we have I mu L equals to IA. Simple one formula you need to follow. I is ampere, A is meter square. By inserting the value of E, H and M and pi also, the electron has a magnetic moment due to its spin in addition to the magnetic moment due to its orbital motion. Now what I am saying, as you know, electron is spinning also. So due to this spinning of electron, we have a spin magnetic moment. As a result, an electron's result magnetic moment is the vector sum of the orbital to the spin and magnetic moments. That is a little bit deeper, but I can teach you guys. L equals to M plus, not this one, L plus S equals to net, and you can say magnetic moment, L, or okay, this one, mu L plus mu S, which gives you electron. I mean magnetic movement of an electron due to angular or orbital rotation, this one is, and due to spin. Okay. Diagrammatically, why should I have you think of this? Like, why should I draw diagram within a second whenever I explain something? Because diagrams, if you understand or if you really understand any particular topic, so you can draw that. I mean, that is the quote of a very famous scientist, Feynman. Okay, so this is your nucleus. So one magnet, this magnetic moment is due to this rotation. Due to which rotation, beta? Due to this, or one is on its axis. One is on its axis. Okay, is this clear? Is this clear, beta Hari? So there are two magnetic moments, but right now we are discussing only orbital one, this one. In the higher classes we talk about this one also. This is due to spin. Clear? Okay. So now this is your question. You know gyromagnetic ratio of an electron in an H atom according to the Bohr model is. Tell me which one is the correct answer. You know now what is gyromagnetic ratio? Magnetic movement of due to orbital of electron or due to orbital electron. It is constant, sir. Yes. So which one is the correct answer? Independent of orbit is in. Okay. Increase with the quantum number? No. Positive, negative. Okay. Everyone, just write the formula for this particular thing, gyromagnetic ratio, in the chat box, and then tell me the answer. Then I'll tell you one important thing what is going to be coming. There is a one, I mean, that is, okay, you tell me this, then I'll answer. Everyone, beta, just write the formula for this gyromagnetic ratio. You are noting down something somewhere, na? Or not? What is the formula for gyromagnetic ratio? Why are you sitting like this? Write it down in the chat box. Everyone. You can directly write in this way, E by 2m already. Okay. So as you know, E by 2m. Say very simple one. But see, right now you know this thing. Okay, one option is C, one is saying C, one is saying D. Okay, let's check which one is the correct one. D. Why we say C? Okay, angular momentum of electron L is given by nh upon 2 pi m. Magnetic moment of electron M is L, which is E h upon 4 pi m. So, how E by 2m is constant. We already defined this, but in a proper written way, if in this numerical value is going to be asked in a subjective way, so then you need to explain this. But as we know, E by 2m is a constant thing, so we can write this L upon L simply. Okay, find this one. Okay, this one is easy, but this one I'm just going to give you a hint, and then we talk about a movie which is going to be coming. A charge Q is separated uniformly. Okay, a charge Q is spread. A charge Q is spread uniformly over an insulated loop of radius r if it is rotated with an angular velocity omega with respect to normal axis. Then the magnetic moment of the loop, very easy it is, believe me if I'm saying so. Okay, Picturization and hint again. Okay, just give you the hint. Charge Q is spread uniformly over an insulated loop. Okay, what is the meaning of insulated loop? Suppose this is your insulated loop and there is a charge spread on this like this. Okay. Now this particular this loop have a radius r. This particular, okay, I need to draw with another color. Is this going to be visible? No. Is this? Yeah. This loop have a radius r. If it is rotated with an angular velocity with, okay, so take this is, and it is rotated with angular velocity omega. Okay. Now find magnetic moment. Very simple. Magnetic moment IA. Find I. A is very easy. Pi r square. Do the thing. So the main thing is finding I. Do that. Tell me, beta, which one is the correct answer? Sometimes my mind. Tell me, beta, which one is the correct answer? A, B, C, D, E. I mean, obviously A, E. We have only one option, A. Other than A, B, anyone find other than A also? And if I'm saying, so please turn on your cameras because I have the power also, but I don't want to do because I'm not doing. Maybe you are doing something else. No, sir, A only. Oh, good. So please don't force me to do that. I can do that, but I don't want to do. Maybe you are doing something what is not necessary to look on this. Okay, but it is necessary for the benefit of yours. Sometimes you are not understanding and you finding difficult to say also in front of all. But the moment I can see your faces, I can read a little bit. Okay, like I read the Hari Mahesh face maximum number of times. He looks frustrated today as well. What happened, beta? Okay, so that's why I'm saying. You get this answer, Hari? Did you solve this? Which one is the correct? One sec, sir. Okay. You are not able to see each other's face, right? Just tell me, because I want to tell you something important. Okay, good. Harry Mahesh look like one of the movie characters. Harry Potter. I'm just kidding. And I believe he is the. I mean, he is. That's why my camera is on. Okay, yeah, that's why. And so A option is correct. Sir, is it A? Yes, beta. A option is correct. Magnetic moment mu equals to IA. I, as we know, E by T, or instead of E, sorry, we don't have E here. We have Q here. I have a very high expectations from you, beta. Believe me on this. Because your feedback is in this way coming to me. The teacher, the physics teacher teach you na before me. Deepak sir, right? So that's why I have a very high expectations from you at least. So Q by T, T is 2 pi, I mean T you know already, T is nothing 2 pi r upon V. Put it down so you can get this. This is your I, this is your A. And the main change we do here, what we are doing, we just putting V equals to R omega, nothing more than that. Clear? So this is your mu QV upon 2 pi R into pi R square. This R and V gives me omega and R square. Okay. One more R I can do that. Okay. Multiplying, I mean putting V equals to R omega. So R cancel and then pi cancel and then we have this. Simple. Now it is simple because it's in the formulation only. What if I can give you the numeric values? For example, Q is something. Okay, meaning of my saying, but I'm wait. If this, I mean this can be, they make it a little bit more complex, giving you two equal this one. I'm just giving you directly, but obviously they don't give you directly in this way. 2 radian. I mean whatever the unit of it, maybe radian if I'm not wrong. Radian per second, right? Theta upon, yeah. So then something value need to calculate also. But obviously something value you calculate when you know the formula. So first is finding the formula, because you cannot learn everything. Even I mean I don't able to learn everything. If you are, so it's good for you. So that is why it is important. Okay. Is this clear, everyone? Okay. So moving ahead. Now we discussed this thing, I think, in the previous class also. So let's revise this in a quick way. Then we go ahead for galvanometer thing. So torque produced in a rectangular coil, rectangular current loop in a uniform magnetic field. I remember, I know this thing. So when a rectangular loop with n turns of area A, each carries a continuous current I and is put into a uniform magnetic field B, so that the loop normal to the plane makes an angle with the magnetic field direction. The loop experiences a torque whose magnitude is given by, I'm not going to derive this formula because I already derived, if I'm not wrong, NIAP sin theta. Clear? I already did this in the previous class. And magnetic moment, the magnetic dipole moment current loop is defined as M, which is NIA. Instead of simple one, what is the meaning? I mean, we just put N. Nothing more than that. Again this one coil, again this one coil, again this one coil. You can imagine like a bunch of Bengals, the girls here. So now you think there are n number of turns, and for their n number of turns, we have this kind of radius. I mean, this is your axis and this is your radius. So you can magnetic moment, instead of IA, we have NIA, National Investigation Agency. You can remember like this also. I remember in this way, if you want to remember. Okay. NIA, National Investigation Agency. Okay, tell me, anyone, what is your main thing to be? Everyone here is wanted to be engineer, or someone have a plan after engineering also, like IPS, IAS, something. Because these jobs are very, you can say, curious, isn't it? You tell me, beta, Shakti. Shakti. Shakti is listening something else. Are you listening? Shakti, beta, am I audible? Am I audible, Shakti? Yes, I'm talking to you. Am I audible? He's not responding. Shakti, am I audible, beta? Speak up. Your mic is not working, so you can type it. Your mic is not working, beta. Ah, good. Type it. I am asking, do you have any other plans after this engineering also? Because engineering is just 4 years. And then what? Like bigger plan, IPS, IAS, something. Because most of the engineers can switch their job after engineering. They can become actor, actresses, singer. Oh my goodness, IAS. What is the full form of IAS? Let's do some general conversation here. Nice to hear this. Sir, if I have confidence means I will try for IS. If I have, what does it mean? You have some digital designing related fields. Nice. Okay, share me or everyone. Beta Parikshit, please don't. Let Shakti let the do his job. No? I'm asking to each particular because that is very interesting topic right now. Why should I ask this? Because uh, I try to be in this, but I find it very late in my life. Like NIA something look like this. After watching this, which one? Family Man. Okay, after watching Family Man, I hope and I believe you each watch that particular web series. Family Man on Amazon Prime. I'm not promoting that, but it's a good one. So after watching that particular Family Man, I find that job is very, you can say interesting, curious. I don't know why. So NIA, National Investigation Agency, IB, Intelligence Bureau, something look like this, in which you do the major work without getting the fame and name. Okay, isn't it? So these are the curious jobs. IAS, IPS are the hardest thing. These are not that much curious, but very responsible jobs. These are. Okay, so just moving this in this, this is comes from NIA from this. So magnetic moment, or you can say magnetic dipole moment of a current loop having n number of terms, you can remember in this NIA. But this is not related to this. Sir, my brother was studying in the top college of Chennai. He studied CS engineering. Okay, got placed. People, oh my god, he quit that study for TNPCS. Okay, Tamil Nadu Public Service Commission. Even years gone, still he can't clear. Yeah, beta, that is I know. Very hard competition. My most of the friends preparing for UPSC also Union Public Service Commission, IS, IPS, IRS, these things, and they are also preparing since last 4 5 years. So it takes time. Okay, so just pass the best wishes to your brother by my side, and told him just have patience. It takes time. It's not something like you can achieve in a day or two. It took years and literally hard working years, patience, so many things. Okay, why UPSC? Because after clearing UPSC, UPSC is the preliminary exam for to be the IAS IPS. Okay, conducted by the central government once in a year only. And then after clearing first round of exam, there is second round and there is an interview process. So there is a large something. There is sometime I'm discussing in great detail when when I have a smaller content and we can say small content on the PPT. Okay. In the coming chapter is going to be, so wait for a while. So the magnetic moment, we discussed this thing already. So the magnetic moment, dipole moment of a current carrying loop can be calculated as the product of loop's current and total area, as simple as that. And that is L into, again it looks like L, but it is I. I into NA. Due to the current in the loop, the magnetic dipole moment is a vector quantity with direction parallel to the magnetic field direction. Okay, this is parallel to the magnetic field direction, and that is a vector quantity. Moving coil galvanometer. Oh my goodness. Directly we come on this. I don't want to teach right now this because I want to teach this thing in a one go. Okay, so we stop here, take a pause a little bit, and we can discuss. Okay, I can discuss one thing which is interesting for you. There is a, maybe you know, maybe you don't. Maybe I can write the spelling wrong also. Christopher Nolan. Okay, he is the one director who create most of the amazing movies, specifically on science-based movies. Okay, see, I give you so many knowledge other than physics also. Science-based movie. SCIENC. Spelling is correct. If my spelling is wrong, please correct me without hesitation. Science-based movies. Why should I write this name? Director who create very good and you can say thoughtful science-based movies. Like if you remember or if you know the name, something like Tenet, Interstellar, or there is Gravity, Galaxy, Martians, movies like this. Avatar also, if I'm not wrong. Okay, so there is one interesting movie which is going to be coming in the month of June. So you can watch it, and there is a open air. I mean, again, my spelling is going to be okay. Let me check the movie name first. And why should I told you to do that? Open air. Give me a minute. This is the name. It is going to be released maybe in coming days. The movie name is OPPENHE Open Mirror. Something look like this. Yeah. This is just hmm, yeah. Wait for a while, beta. This is the exact name. I want you to watch this. Why so? This one is based on, I mean, it's hard to understand at your level, at my level, and maximum people's level also. But it is based on the famous incident based on atomic bomb, if I'm not wrong, because I don't watch the movie still, or World War II. World War II. In this particular scenario, there is a great disaster, not great, worst disaster. Sorry, I'm saying great. Oh, second great. There is a worst disaster happening in Japan, Hiroshima, Nagasaki. Maybe you remember this name. So that particular movie is based on that atomic bomb in World War II, where all the renowned or you can say famous scientists, you can say hijacked and they placed on our one place. Okay, so this is, you can go after this. I mean, in the break also you can watch the trailer. If you like it, watch it. Why should I say to watch it? Because once you watch these kind of movie, which is specifically science-based movie, so then you know the importance of science, specifically physics, in more great detail. Okay, and that particular director, this is the name of director. The director makes really good movies, specifically on science-based. Okay, Christopher Nolan. If I find something in Bollywood, so I can tell that also. Is this clear? So if you interested in watching movies, so watch these kinds of movies too. Just information pass. Okay. After a break, we discuss this thing. So there is a break now, not more than 10 minutes. Okay. You guys go and drink water, take a break a little bit, and then we discuss about. I already maybe discussed, but in one of the numerical, not in a proper way. So that is really important. Okay. Hello, hello, hello. Am I audible? Hello. Am I audible? Am I visible, beta? Okay, just a little again once. I'm telling you so many students today. Nice to see this. Sorry. So this particular device, this is a device moving coil galvanometer, and obviously this is going to be dependent on two things like torque. What is the meaning? Like it is a normal device in which is going to be used as a voltmeter also, which is going to be used as a ammeter also, maximum number of times, and it is based on the effect of a torque whenever there is a current coil or whenever there is a, you can say, conductor in any particular magnetic field, uniform magnetic field. So we see that particular torque effect, and due to that particular torque effect, like sorry, in speedometer, suppose this is your speedometer in your bikes or in your cars, right? And there is a one needle. This is your center, and from the center, okay, just a minute, and we have particular proper diagram in the next page. So this is going to be rotate. I mean, this particular thing, this particular needle is going to be rotated, and there are the numbers, right? So we can use this particular device on the basis on the particular subtopic of turning effect of current coil, or you can say torque in a current coil in an uniform magnetic field. Okay, so this particular device is a moving coil galvanometer, in which this particular coil is going to be moved, and this movement creates the torque, and due to this torque we have that particular number, or you can say measurement, 1 2 3 4 5 6, and this particular moving coil galvanometer can be converted or used as ammeter. What is ammeter? Ammeter is an instrument, or it is a device which is going to give you the measurement of current. Is this clear, everyone? Just turn on your cameras, beta. I don't know how many times I need to say this. Okay. So a moving coil galvanometer is an instrument for measuring electric current. It is a sensitive electromagnetic gadget. Electromagnetic gadget means what? What does it mean? Means whenever you have an electron, or you can, sorry, whenever you have an electric current, so only and only then it is going to produce the magnetic effect. So that particular thing is a electromagnet, or you can say that can detect extremely low currents due to a few, down to a few microamperes. So as you read it out, as we read it out, moving coil galvanometer is used. It is very important, and it is used to measurement of the low current. Low current means in up to the range of microampere. What is the meaning of microampere? Microampere is 10 to the power minus 6 ampere. Okay, so these small currents can be obtained, can be measured by this. There are two primary types of moving coil galvanometers: a galvanometer with suspended coils, a galvanometer with a pivoting coil, or a Western galvanometer. These are the names. There are two types of galvanometer. Let's discuss this one by one. So first of all, what is the principle? I already discussed this principle. This is in the written form, nothing more than that. So principle of a moving coil galvanometer: the magnetic torque is experienced when a current coil, or you can say current carrying coil, is put in an external magnetic field. The angle through which the coil is deflected due to the magnetic torque effect is proportional to the coil's current magnitude. What it is means, suppose you have this particular coil. In this particular coil, we have this magnetic field. Suppose this time magnetic field is in this direction, but it is uniform. Okay, it is in this particular form. Now, this particular current carrying coil, there is a current in this. Suppose I apply a current in this way. So this is going to rotate because it is in the uniform magnetic field B, and whenever a current is going to be rotated, so it generates a magnetic field of its own. So due to this, and there is a magnetic force also. So it is going to rotate uh, wait in this way. Okay, so this is the concept, this is the principle of a moving coil galvanometer. And torque equals to m cross b sine theta, NIAB sine theta. We already discussed this thing, right? In the previous class, in the previous slides, already we discussed the torque, which is m cross b. If you don't remember, so torque is nothing but m cross b. M is magnetic moment, so it is going to give you mb sine theta. And you can put NIAB because M is a magnetic dipole moment, which is NIA. So that is NIAB sine theta, nothing more. That is your torque, and it is a fractal quantity. Is this clear? So we discussed this thing on the principle of that this particular important, you can say, instrument is working. Moving coil galvanometer. Clear, everyone? Is this clear now, everyone? Good. Then moving ahead, this is the construction, or you can say, as you can see in this particular picturization. Okay, first let me point out some values. So it is very clear. It is a scale where we are going to find the number of, you can say, measurement of micro range. This NMS. Okay, so this one is a magnet of yours. Okay, this is a pointer, very easy to understand. Pointer is just a, you can say, in this particular thing, pointer is like a deflection, or you can say coil, which is going to give you. Here we have soft iron core, or you can say soft iron core, just for uniform radial magnetic field. Just a minute. Okay, and this is your pivot. Pivot is going, what it is means it is going to rotate whenever we flow the current, because it is a coil. So whenever we flow the current in the coil, so this particular coil is behaving like a magnet, and it is already in a magnet, so it is going to rotate. Is this clear? Because it is somehow a same thing. Your current carrying coil, or you can say, wait a minute, these are your current carrying coils, are situated in uniform magnetic field. Uniform magnetic field, what it is mean, beta? From north to south. If I am going to draw in this way, so this, okay. I mean, obviously these are not representing like this, but uniform magnetic field, you can draw this. Simply, if you have a magnet in this way, just a minute. If you have a magnet in this way, so you know from north, this is your north, this is your south. From north to south, it is going in this way. From north to south, it is going in this way. And then from it is, I mean, in this way. This is your magnetic field line. Okay, this is your north, and this one is your south. So from north to south, from north, your magnetic field lines is originating. So this is just a pictorial diagram for this moving coil galvanometer. Okay, so you can say pictorial representation of galvanometer. Is this clear, everyone? Nothing as such you don't know. Clear or not? Just write it down. Is this clear with everyone? Good. Okay, so this is your working. Just read out our working once, and it is easy. Just keep remind, or keep understand this thing, not remind yourself. Understand this very basic thing. Whenever any particular current coil is situated in a uniform magnetic field, so it generates, I mean, it feel a torque. As simple as that. Whenever we apply, or whenever we give the current to the coil, simple as that. So it feels a torque, and due to this torque, that is going to rotate. So this rotation we terminate. This rotation is going to be we measure. So we reverse this scenario now. If we have a rotation in any particular coil, whenever we apply the current, so we can measure that particular current on the basis of that particular rotation. What rotation? This rotation. Suppose this particular, you can say, pointer, instead of this, you can find here somewhere after a little bit rotation, and this is your range for millimeter current. Suppose 1, 2, 3, 4, 5, 6, 7, 8. mm, or you can say ma, milliampere. Okay, so you can find it down. What particular, I mean, initially it is, you can say 1, 2, and now it is at 4. Simply. Is this clear, everyone? So the moment we apply a little bit current, or the moment we see this particular deflection in this, like my finger doing right now, or very simple basic thing like a speedometer. You can uh, see this in limited edition of bullets right now, or in few cars, because nowadays everything is going to be digital. Your speedometer are also are digital nowadays. But in few motorcycles, bikes, or in few cars also, the pointer is going to denote the how much fuel you have. That is also look like this. Clear, everyone? Or moreover, you're going to see this in your laboratory. So allow me to pass through. That is very easy. Working is just the whole soil formation. Allow me to pass through a rectangular coil with n number of turns and area of A in cross section. When the coil is placed in a uniform radial magnetic field, radial means it is going to be in the radius form. Radial magnetic field B, it experiences a torque, as we know this. Consider a rectangular coil with a length of L and A width, length L, A width of B is in a single turn, ABCD. That is going to be situated and drawn in the next page. The coil is suspended in a magnetic field of strength B with the same plane of the coil parallel to the field. The sides AB and DC are not subjected to any magnetic field effective force, magnetic field effective force, because they are parallel to the field direction. The perpendicular to the field direction side AD and BC are adjusted, so an effective force F, which is given by IBL sine theta, and that is, I need to write it down, F equals to force, which is IBL sine theta. So here sine theta is going to be converted into 1 because it is perpendicular. So torque is nothing, force into perpendicular distance between two forces. Torque tau equals to F into B, and that is L into B gives me area. That torque equals to NIAB. I already discussed this thing, and let me check where is the diagram. They don't give you the diagram here. Very bad. We need to view this diagram. So you can understand from this one also or this one also, as simple as that. Okay, suppose there is a, but I already do this thing, A, B, C, D. So in in these branches, right now I draw this particular thing in a little bit tilt, but in AB or CD branch, we cannot have any particular force because of these are in perpendicular, and magnetic force, we know this, I, B, magnetic field, L sine theta. So due to this theta, when this length element and is this magnetic field are in the same direction, then this force is going to be 0. So that is why written here, like the side AB and DC are not subjected to any magnetic field. Okay, visualizing this AB and CD, or you can say DC. Perpendicular to the field direction, AD and BC are subjected an effective force. This one again, yeah, I can know that. This AD and BC, the perpendicular to the magnetic field, as you can see a little bit, not properly because I tilted my magnetic field a little bit. So we have IBL sine theta, and sine theta is, sorry sir, I got disconnected. It's okay with that. Okay, so moving ahead, this is the torque. I already explained this thing, torque, in the previous slide. Not in the previous slide, in the previous class also. So that is not a big problem, NIAB. The main thing is in the advancement. The coil rotates as a result of the magnetic torque. Okay, this coil is going to rotate. Just give me a minute. I can draw, I can copy paste this thing. Yeah. Just a minute. Just a minute. So as which particular coil is going to rotate? We are talking about this particular coil, which is situated here. Okay. Yes. So the coil, as a result of the magnetic torque and the phosphorus bronze strips twist. This is your phosphorus bronze strip twist. The spring S is linked to the coil. This spring, as you can see, linked to the coil, in turns provides a counter torque on restoring torque K. This resulting in a constant angular deflection. What is the meaning of this particular lines? Due to this particular torque effect, this spring is going to turn, this spring is going to give me the rotational effect, which is torque, and due to this torque there is a twist in this particular line, in this particular pointer. There is a twist in this particular pointer, and this twist gives me with this particular angle. Suppose initially it has 0 angle, and now from here to here it covers theta angle. So there are two torque. One is due to this magnetic field, or due to this current carrying coil, or due to this coil in the magnetic field, and due to the response of this torque in this particular pointer, we have a torque also. So both the torque is going to be rotated. Okay, is this clear, everyone? For example, the more amount of force or rotational force you apply on a particular, this is somewhere analogous to like this. Suppose this is your door, and on this particular door, just give me a second. These are the hinges, and this is your wait a minute, beta. This is your door handle. So the more force, or force instead of force, the correct word is, the more torque you apply here, the more it is going to be rotated, your door. Is this clear? So in the same way, the more torque is applied here in this particular spring, so due to this spring attachment, this more torque is going to be generated in this, the more constant angular deflection, or due to this restoring torque, we have a constant angular deflection. And the more deflection we can see, the more fine, or you can say the more deliberate moving coil galvanometer we can make, which can able to denote, which can able to measure the current up to the range of microampere. Is this clear? The wording, because right now after this wording we have a formulation. Is this clear? As simple as that. Whenever you open or close the door, so you apply a force on this particular door handle. Okay, and this is your force in general. That particular arrow is nothing but a force. Okay, wait. Torque is this. This is your force, and this particular force and this particular perpendicular direction gives you torque, which is R cross F. This is the general formula. The more torque, the more it is going to rotate. Is this clear? Clear now, everyone? The more torque you are going to apply, it means the more force you are going to apply on a door handle. For example, if there is a door, a bigger door, so that particular bigger door cannot open by a small baby or very old ones, because they are not able to apply that much force on this particular door handle. But younger ones, or you can say adults, can do that. So as simple as that, the more torque is generated here in this particular range, the more torque is generated here, the more this particular pointer is going to deflect in a very fine way, or we can observe the very low amount of current. Low amount of current means a little bit amount of current can generate the torque here, and due to this torque, in the reverse of this, it can deflect a little bit also. Okay, and this deflection we can going to observe. We are not going to observe this torque. In the response of this torque, we are going to observe the deflection in this particular coil, and that is the constant angular deflection. Is this clear? And due to this deflection on this particular scale, here we can find the milliampere or microampere range current. Is this clear, everyone? Because if you understand this, whatever I am saying right now, after this everything is formulation, nothing more than this. So clear or understanding? better understanding or more understanding is more important as compared to learning the formulas. Should I explain again? Tell me everyone, is this clear beta? Then I move ahead. Because if this is clear, so then everything is easy. Working is we are talking all about. Good. So as we know, under the equilibrium condition, what is the meaning of saying that? Under the equilibrium condition means when this particular torque due to NIAB, sine theta, you can say NIAB only, in the NIAB, this torque is due to the magnetic field in a coil, and then one torque is K theta, or you can say K is constant of this particular deflection, or you can say of the pointer, and I mean K is depend on the how much it is conductor, how much it is going to show you this particular thing, and then theta is the angular constant. Okay, so K theta equals to NIAB, both the equating both the equation, because it is in the equilibrium condition, equation number 1 or equation number 2. So under equilibrium condition means equation 1 and 2 going to be equate, where K is the torsional constant of the spring. I mean that is particular thing is the torsional constant of a spring denoted by the letter K. Is this clear? Restoring couple per unit twist. The deflection or twist is measured by a pointer attached. This is your deflection measured by a pointer, or wait a minute, this K is give you this by this particular spring. This particular spring, this one. So K theta equals to NIAB and then theta. The main aim of everything, whatever we are discussing since last 10-15 minutes is this. Okay, so theta is dependent on what? The more the number, the more refined theta or more angular displacement you can find. More the length of a, you can say, conductor or this particular current carrying coil, a magnetic field, or inversely proportional to K. So in general, we took this NAB upon K constant. Okay, A is the area of coil, N is the number of coil, B is the magnetic field, K is the spring constant. We fix the spring. What we can change easily? L, length of the spring, isn't it? This L is length of the spring. Not, this is not LE, this is A. This L and A confuse me a lot. This is I. But, wait. N, I, A, B. So we fix everything like A, area of a coil, length into that, K is spring constant, and on just changing this N, changing this I, which is a current, we can find very small deflection even for very small current. Okay, so theta directly proportional to I, which is current. For a given galvanometer, the quantity NA by B is constant. As a result, it is clear that the deflection of the galvanometer is proportional to the current flowing through it. Is this clear, everyone? Making this N number of turns in a coil, A area of coil, B magnetic field, and K spring constant. We can make every particular thing initially, because once we make this particular moving coil galvanometer, we fix these things. Now what is the changeable thing? I, current only. Is this clear? So this one is important. Theta is directly proportional to I, and from where it comes, this theta equals to NAB upon K into I. Why we put this thing into the bracket? Because we see we make it constant, making fix this thing. I mean, we fix these things, and a number of turns, A area of coil, B you can say magnetic field, K spring constant. Spring constant, you know na, how much it is going to compress, how much it is going to give you the extension, or how much it is going to give you the twist the moment you rotate it. Clear everyone? Or should I write these things also? I just write this spring constant. Everything you know. Area of a coil. Okay. Okay, then I can write B also. Magnetic field and number of turns. Number of turns. What remaining? I. I is the important thing. I. Current. Okay. So this is your important relation. Is this clear, everyone? Okay. So the more torque we have, which is NIAB, so the more deflection we can observe easily. More deflection gives you smallest current. And this NAB by K is a constant thing for moving coil galvanometer. So now sensitivity of a moving coil galvanometer, what is sensitivity? D theta upon di means how much deflection you can observe for a minute change of current. That is your sensitivity of a moving coil galvanometer, and it is important. Okay, this sensitivity is nothing but beta simply this. You can remember, not remember, you can understand in this way: how much deflection, how much deflection galvanometer gives, galvanometer gives for minute current also. Minute means very small, or very small current. Okay, that is the meaning of this. The ratio of, or the proper understandable, or you can say the proper scientific terminology, the ratio of change in deflection of the galvanometer to change in the current in the coil is the broad definition of a sensitivity experienced by a moving coil galvanometer. Or for better understanding, how much deflection galvanometer gives for very small current. That is your sensitivity. Clear na? The more sensitivity, the more proper work is it can do, the more smaller current it can observe. Clear everyone? For example, if you have a centimeter scale, so you can only and only observe the centimeter thing. If you have a vernier caliper, so you can go to the millimeter. But if you have a screw gauge, so you can measure the micrometer also. Clear? 10 micrometer, 100 micrometer, 50 micrometer. Clear this thing, everyone? Good. Then moving ahead, we have a current sensitivity and we have a voltage sensitivity. So that is important again. If we can observe the current or measure the current, so easily using V equals to IR, we can observe the voltage also. Okay. What I'm using using V equals to IR, we can observe voltage also. So if a galvanometer shows a large deflection for a modest amount of current, it has a higher sensitivity. Current sensitivity and voltage sensitivity are the two types of sensitivity of a moving coil galvanometer, or from a moving coil galvanometer we can understand. The deflection theta per unit current I is known as a current sensitivity. Theta upon I is NAB by K, as simple as that. Okay. And then voltage sensitivity theta upon V, the amount of deflection theta per unit voltage, theta by V. And this is very easy. Instead of okay, as we know, theta is NAB upon what I'm writing NAB upon K into I. I have I, so I equals to V by R or V equals to IR. So from I need to find, okay, instead of I, what I can put, theta equals to NAB upon K into V by R. This is my formula, and from here I can go like this: theta by V, which is a voltage sensitivity, NAB upon K into R. So you can remove that, or instead of this, you can write this NA. Clear? Because instead of I, simply I can put V by R from here. As we know, I equals to V by R, and I know voltage sensitivity is theta by V. This is very simple. I just rearranging the formulas. Nothing I'm doing more. Can you just show the previous slide? This one. Okay. So sensitivity of a moving coil galvanometer is theta, d theta upon di, and there are two types of sensitivity: current sensitivity and voltage sensitivity. Josna beta, you can see after the class also, because that is nothing much important is written over there. Factors affecting the sensitivity of a galvanometer, as we know, there are the factors: number of turns in the coil, N, area of the coil A, the strength of the magnetic field B, and that is A upon N. AB is the magnitude of the pair per unit twist. Okay, so these are the factors affecting the sensitivity of a galvanometer. As simply we we talk about current sensitivity and voltage sensitivity all together. So current, what happened to my writing today? Current sensitivity, and that is I, as you can write, theta by I, and that is nothing but NAB upon K. In the same way, I can use that now. Voltage sensitivity, that is Vs theta by V, and that is NAB upon KR. R is resistance. R is resistance. Okay, so using this we can find this. So it is obviously dependent on K and A and B and R also, if we're talking about voltage sensitivity. Application of a moving coil galvanometer, we already know this thing. So let's quickly you can say go through this. Because of moving coil galvanometer in such a sensitive, it is such a sensitive instrument, it is maybe used to detect the presence of a current in any circuit. First of all, when a galvanometer is used in a Wheatstone bridge circuit, the pointer in the galvanometer exhibits no deflection, indicating that no current is flowing through the device. Depending on the direction of the current, the pointer deflects to the left or right by connecting it in parallel to low resistance that can be converted into low resistance ammeter. And if we can convert or if we can connect that particular galvanometer in a series, so we can convert it into voltmeter. Okay, so we can see that on the next page, if I'm not wrong. Yes. So conversion of a galvanometer into ammeter, we discuss this thing in a very refined, in a very short way, in any particular numerical value, in any particular numerical problem, if I'm not wrong. So this is your galvanometer. If it is converted into this way, into the parallel resistance, shunt resistance, this is known as Okay, this S here beta is nothing but shunt resistance. Shunt means very small resistance. SHUNT, shunt resistance. Shunt resistance, or you can say very small resistance. So if it is in this way, so it behaves like a ammeter. Nothing more than that. IG. So obviously this is going to be I minus IG. Here we have a voltage drop which is S into I minus IG and G and then again I. So let's now consider RG, the resistance. Okay, this is your resistance of a galvanometer. As the resistance of the galvanometer G and galvanometer coil L. Again this I represents the total current passing through the circuit. IG is the current, or you can say represent the total current passing through the galvanometer, which corresponds to full scale reading. RS is shows the value of a shunt resistance. Okay, this RS. Moving ahead, as we know in what we know, IS equal to I minus IG. What it is? Yeah, we know this. Or you can remember it, but remembering anything here. I total current is IS, which is the current in the shunt resistance, plus IG, the current in the galvanometer. So from there, IS, current in the shunt resistance, is nothing but I minus IG. And let me remove this. I minus IG. Okay, the current via the shunt resistance when the IG passes through the galvanometer is given by this. Due to parallel nature of their connection, the voltage across the galvanometer and the shunt resistance are equal. We know this thing. This is your galvanometer. Okay, and this one is your shunt resistance. So in any particular circuit, beta, we have parallel. I mean, in any particular circuit, which in any particular devices which are applied in a parallel connection, so the voltage is going to be equal. So obviously voltage which is VG, that is nothing but IG into RG. Okay, and that is IS into RS, which is VS. So we are doing that. Nothing more we are doing here. New I. Is this clear, everyone? We know this thing and we discussed this thing long back ago, if you remember, in electric current chapter. Okay, so we are just revising this thing, and then so okay, from here what we can find, so many things. First of all, the maximum number of times they find RS, which is RS, resistance of a shunt resistance RS. This is going to be directly, you can use so many formulas. VG, galvanometer voltage of a galvanometer, I minus IG. Okay, and you can write this thing also, IG into RG divided by I minus IG. So I can write one more formula from here itself. RS, if I take IG common, right? So it is going to be RG. I, if I take common, so I divided by IG minus 1. You can create so many formulas, whatever the formula is required. And obviously, IS is I minus IG. So on behalf of that, on these particular 2-3 formulas, you can find anything. Means, if you have a resistance of this particular thing, which is a moving coil, I mean shunt resistance, so you can find the current here also. Okay, is this clear? So these are the particular things, a maximum number of times in any particular numerical value, you need to find it out. Nothing more than that. Moving ahead, conversion of a galvanometer to voltmeter. Just apply a high value resistance directly into the series connection of this. This is your resistance directly applied to the galvanometer. So now current is going to remain same. On the basis of that, we can do the things. V equals to RG into IG plus R into IG. R is the resistance or large resistance of this thing. and obviously Ig is going to be remain same because in series connection current is going to be remain same. Okay, so let's now consider Rg as the resistance of a galvanometer. Again, G as a galvanometer coil, I represents the current total passing through the circuit, Ig represents the total current passing through the galvanometer, which corresponds to full scale reading. V shows the voltage drop across the series connection of galvanometer, and high resistance. The voltage drop across the branch AB is given by when current Ig travels through the series combination of galvanometer and the high resistance R. So this is how, I mean, this in this way you can find the voltage for the from the use of galvanometer, and these are the applications. So advantage of a moving coil galvanometer are provide high sensitivity. Stray magnetic fields have the little effect on it. I mean, very with the help of very minute magnetic field you can find the current also. It has a high torque to weight ratio, high precision and dependability. Disadvantage of a moving coil galvanometer are only direct currents can be measured using it. You cannot find the AC one. Okay, this is one of the main advantage. Disadvantage of causes such as an instrument aging, permanent magnets and mechanical stress damage to the spring. Due to the damaging of the spring after the using that particular instrument device again and again, we can not find the appropriate or accurate precise value, and we cannot find the AC also. AC current cannot measure. Okay, so do this one. A galvanometer of resistance. Okay, a galvanometer of resistance G is converted into a voltmeter of range 0 to 1 volt by connecting a resistance R1 in the series with it. The additional resistance R1 is in series. The additional resistance that should be connected in series with R1 to increase the range of the voltmeter from 0 to 2 volt will be. Find the correct answer. A, B, C, D. Do that, beta, because after that we have very not that much important, but if D. Okay, yes, it is D. Everyone see that. So galvanometer resistance G is converted into a voltmeter range of 0 to 1. So V equals to 1, which is Ig, G plus R1. This is your first equation. To increase the range of voltmeter 0 to 2. 2 equals to Ig into R1 plus R2 plus G. So dividing equation 1 by 2, so you can get this. R2 equals to nothing but G plus R1. So the correct option is D. Do that one also. See, we are sorry. We have one more important learning concept in this class right now also. So let me do a little bit quick. Okay. That is not that much important, but it is important if you get a difficult paper. Believe me on this. So a galvanometer whose resistance is this much ohm has a deviation this much in it. When a current of this much is passes through it, its needle pointer deflects by 1 division. Okay. To use this galvanometer as a voltmeter of range this, it should be connected to a resistance of this. See, I is given, division is given, the resistance of a galvanometer is given, and theta is also given. So you need to tell me the resistance which is need to connected to convert this particular galvanometer into voltmeter, and this is your voltage also. Then division is given. This is a galvanometer who has a resistance Rg, resistance of a galvanometer. Okay, current is given, and then you can find the, obviously current is given, so everything is given. Do that. Should I discuss this? Okay, let me do this because galvanometer has a 25 divisions of Ig. So first of all, we need to find the current. Ig equals to this for one division. There is the catch. So 4 into 25. So that much current you have. What is the meaning of this? This much division you have, and Ig is always the current where we this particular needle. Okay, wait a minute. This particular needle shows the full deflection, this deflection. So suppose from here we have a 1, 2, 3, 4, 5, 6 dot 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 25 divisions. For one division we have a this much. Okay, so then V equals to Ig into R net. R net is nothing, G plus R. We need to find R. So from very easy method, R is 200 ohm. Is this clear, everyone? The main catch is here in finding Ig. Clear? Is this clear with everyone? Good. Now this is one of the another type of galvanometer, not that much important, but if you are, I'm not saying unlucky, but if you face a difficult or more than if in any particular case the physics paper is going to be make more than moderate or a difficult paper, then you getting this particular kind of questions also. So that is necessary to glance once and go through once. Clear, everyone? Okay. The everything is going to be remain in the same way, the principal concept, but few things is going to be changed right now. So let's discuss this thing also. Tangent galvanometer. It is an instrument used to measure very small currents. It is a galvanometer with a fixed coil and moving magnet. In the previous thing, we fix the magnets, and there is a radial magnetic field, and the spring is, or you can say coil is going to be fixed. Here the change, or here the reverse is, coil is fixed and magnet is going to be moved. As simple as that. It is based on the tangent's law. Initially, coil is made vertically by leveling screws, and coil is brought in magnetic meridian. Okay. Let's listen this. See this. When you know more about magnetic meridian or magnetic plane in the next chapter, you understand. You watch or rewatch this particular, you can say, lecture again, and then you understand in a better way. Because right now you are confusing in so many things. Like this is what it is, tangent law, BH equals to, magnetic field B equals to BH tan theta, where BH is nothing. Magnetic field due to the horizontal component. What is the general meaning? Suppose this is your, just give me a second. This is your magnetic field in any particular range. So this is your BB, vertical component, this is your BH, as simple as that. Okay, and it is tilted to this theta. So it is B sine theta, and BH is nothing, horizontal component, B cos theta. So this is meridian, and so many things we are going to understand in the next chapter, because right now I cannot teach those many things. So BH and this I can teach you. Okay. So B is produced, which is perpendicular to the plane of coil, Now BH is in the plane of coil, and this BH is in the plane of coil. What is the meaning of this? Suppose I draw my coil in this way. So this is in the plane of coil, not this B, not this BB. Okay. So moving ahead, B equals to BH tan theta or mu naught Ni upon 2A BH tan theta, magnetic field due to a coil, which is mu naught is for permeability and is number of turns, or for any particular circular thing we have a magnetic field for n number of turns. B equals to n mu naught I upon 2A, where A is the radius. Where A is the radius. Okay, this is your A. So we have this magnetic field. So mu naught Ni by 2A, which is magnetic field, BH into tan theta, or I current 2A upon n mu naught BH tan theta, where BH upon G1 tan theta, or this particular BH upon G1 we put K tan theta, where G1, or you can say galvanometer constant, is n mu naught upon 2A. Why so? Because n is number of turns, mu naught is permeability, that is constant. Mu naught you guys know, 4 pi into 10 to the power minus 7. Okay, Weber per meter square, and n number of turns at 2A. So that we can put constant, which is known as a galvanometer constant. And K is BH upon G1 is reduction factor of a galvanometer. Moving ahead, sensitivity. As we already discussed, there are two types of torque. This one torque, K theta, and the other torque is NIAB. Okay, so the same thing we're going to follow. The change, the catch here is, in that particular normal moving coil galvanometer, the coil is going to rotate, magnetic line is going to fix. Here magnetic field is going to rotate and coil is going to fix. Is this clear, everyone, or should I write it this thing? Wait, just give me a second. Here magnetic field is rotating, and that is why we are talking about this tan theta component, and coil is fixed. Is this understood now? Clear? In the previous moving coil galvanometer, as its name suggests, coil is going to rotate, and due to we have two torque, K theta, and that is NIAB. Here we have, instead of moving coil, we have a moving magnetic field. Okay, magnetic field is rotating, so we can find that magnetic field B equals to BH tan theta, and I, because B equals to mu naught Ni by 2A, so I, because initially or finally we have this relation, theta directly proportional to I. So that is why we are doing everything. So sensitivity, a tangent galvanometer is both sensitive and accurate if change in its deflection is large for a given factor, change in current. So I equals to K tan theta, or Di equals to K sec squared theta d theta. That is just differentiation. So Di by I, or you can say change in current upon I, is nothing but d theta change in deflection upon change in theta, which is sin theta cos theta. That is simply a mathematics relation, so I'm not going into that depth. But as we know, I equals to K tan theta here, and sensitivity is what? Di upon d theta, right? So if I am doing the differentiation in both the sides, so K equals to sec square theta d theta, or in general, what is my sensitivity? D theta upon di, change in deflection to the change in current, or you can say d theta upon di, or di by I initially, you can say change in small current to the per unit current, change in small deflection to the deflection. When we do this everything, so d theta becomes sin 2 theta upon 2 into di by I, or d theta equals to d theta max, when sin 2 theta equals to 1, so sin pi by 2, which is theta equals to pi by 4. So the tangent coil galvanometer has a maximum sensitivity at theta equals to pi by 4.